Hi, today we're going to be reviewing chemical messengers. And the ones we'll do in this video today are the cyclic AMP second messenger system, the calcium calmodulin system, the tyrosine kinase system, as well as the phosphatidylinosydyl second messenger system. So, first we'll start off with tyrosine kinase. And tyrosine kinase, the ligand binds to its receptor. This causes the receptor to undergo a conformational change and it becomes an activated enzyme, also known as tyrosine kinase, and this will cause physiological change. Here we have our ligand floating to its receptor, causing the conformational change within tyrosine kinase, and this enzyme causes physiological change. Next, we have calcium calmodulin. Here the ligand binds to its receptor. This causes a conformational change and it becomes a calcium channel. Calcium will flow into the cell and this will act as a second messenger binding to calmodulin, forming a calcium calmodulin complex. And this complex is going to activate protein kinase, which in turn will cause physiological change. Here we have our ligand floating to its receptor, causing a calcium channel to be made within the protein. Calcium flows out and can change the electrical property of the cell, stimulate muscle contraction, secretion, or it can bind to calmodulin, form the complex, and activate protein kinase, which will in turn cause physiological change. Next, we have the cyclic AMP system, where the ligand binds to its receptor, now activating a G protein. The alpha subunit of the G protein binds and activates adenylate cyclase, which will in turn convert ATP to CAMP. And as a second messenger, CAMP will activate protein kinase A, and pKa will cause physiological change. Here, our ligand is binding to its receptor, causing the alpha subunit to dissociate from the rest of the G protein and bind to adenylate cyclase, which in turn converts the ATP into this CAMP, and CAMP will activate protein kinase A, which will in turn cause physiological change. Next, we have the phosphatidylinosydyl, where the ligand binds to its receptor, also activating a G protein. The alpha subunit will bind and activate phospholipase C, and PLC is going to convert PIP2 into DAG and IP3. And in DAG, this will activate protein kinase C, and PKC is going to phosphorylate proteins, resulting in physiological change. Simultaneously, IP3 moves into the cytosol and causes the release of calcium from the endoplasmic reticulum, and calcium will stimulate contraction, secretion, or bind to calmodulin and cause physiological change. Here we have our ligand binding to its receptor, causing the alpha subunit to bind to phospholipase C and convert PIP2 into DAG, which will in turn activate protein kinase C and cause physiological change. IP3 will move into the cytosol and find its receptor, causing a calcium channel to open on the endoplasmic reticulum, and the secreted calcium can result in change in the electrical property of the cell, muscle contraction, secretion, or it can bind to calmodulin again and form the complex to activate protein kinase and make physiological change.